Yes, guys, we were talking about Hermite Bezier curves. We didn't start discussing B-Spline curves. Today, if you have time, I think I may jump into B-Spline curves. But let's see our pace. And skipping these parts, we discussed the introduction that splines are highly important in different fields of science and engineering, in computer graphics, in computer-aided design. We have different representations depending on, let's say, the types. You may classify them according to these properties. And in the earlier days, uh, we started to use these splines, especially in mechanical designs. And firstly, they use flexible metal and kind of packs to have such smooth curves and surfaces. And now we are trying to do it on the computers, and we use a similar approach. Instead of fixed packs, we make use of control points, and instead of actually minimizing the curvature physically, we are using smoother functions, and with the help of it, with the help of them, we can have much better splines. And we have usually piecewise polynomials. Here you see this is a kind of a cubic spline. We have 3 segments, and for each segment, we have different coefficients, but we use the same basis functions. And we have discontinuities obviously at these connection points. And depending on the type of spline, you may have C1 continuity or C2 continuity. It's up to the basis functions you are using. And then we discuss some coordinate functions. This is a spline and X coordinate function, Y coordinate function. And while obtaining kind of any intermediate point on the spline, we make use of the control points and the basis functions. By multiplying them, we can obtain any point on the spline. And on the other hand, we also discuss interpolating splines and approximating ones. This is an interpolating one. As you see, the spline passes through all the control points. But if it's an approximating one, as you see, this is not passing through the control points. It's just passing through the start and the end points. And this is not a must for nerve curves. We will see we can have the start maybe at this point. It doesn't have to start exactly at the first control point. These are some examples: interpolating function, approximating ones, and on the left-hand side, we all have interpolating representations. And they said that these curves are actually linear functions of their controls. It's an highly important issue of the spline curves, which means that if you move the control point 2 units, let's say to the right, and then our x of t will obviously move twice as far as it's moving by 1 unit. So let's say if you are moving your control point to the right by 1 millimeter, then let's say your x of t may move somewhere else, let's say 2.5 millimeters. And if you double your movement, let's say once you move 2 millimeters, then x of t will move twice the amount it has with the 1 unit of movement, which was 2.5. Now if you multiply with 2, x of t should move to that direction by 5 millimeters. So this is the linear relationship between the controls and the resulting, let's say, spline. So we can say that our x of t or y of t, or we can simply say the spline is a linear combination of the control points. This is the fundamentals of splines. So in this chapter, we are going to spend actually more time on different types of curves like Hermite curves, Bezier curves, splines, other nerve curves. Now let's start from the primitive ones. These are linear segments, as you see, piecewise linear case, and the vertices are all control points. And obviously, in each segment, we have a linear function. And you can represent it with such a simple equation. And the constraints are obviously at the endpoints, at the start and end points. By using them, you can represent in different form. So if this is starting point, which is x0, endpoint is x1. So if you put, let's say, t as equal to 0 in this equation, then you will see that the starting point is equal to, or let's say t is equal to 0, our x of t, x of 0 will be equal to simply b, and this is equal to x0. And for t equals to 1, our x of 1 will be equal to a plus b, right? And I know that b is equal to x0, and on the other hand, this one is the last point, the ending point, x1. So we can simply represent a as equal to x1 minus x0. So here what we do, what we have done, we represent this equation in terms of control points, since these are our control points. We don't want to use an extra variables. This is, let's say, x0 and x1. And for the other curve, this is x0 and this is x1. So you may use such conditions to find the other relations, other variables. Yes, this is the vector formulation. The same equation, the same relationship is represented in a different form, in vector form. Any points on the curve is represented with the difference between their start and end points times the parameter plus the starting point. We can also do it in matrix form. Here you see, for instance, we have the control points. These are control points, and we want to use them as a variable. And this is just some, let's say, equations, some polynomials depending on the parameter t. So this is 1/2 matrix. The other one is 2/2. So at the end, we will obtain 1/2, and that will, and finally you will multiply with P0 and P1, which is 2y1. So at the end, we're gonna have a single, let's say, 1/1 result, and that will be the representation of a specific point when t is equal to some value. And let's focus on some formulation regarding the basis functions. Basis functions are important since in the upcoming types of curves, we always refer to basis functions. And once the type of basis functions change, then that means we will have a new type of curve. Hermite basis functions, let's say Bezier basis functions. We have some relations between them, but they are a bit different. Now, in order to obtain these basis functions, what we are doing, we are again using the same equation, but this time we will be regrouping them according to P, not according to T. This is the result. Now I can represent it again in terms of matrix formulation, but as you see, it's the same. Just the thing is that we need to multiply this part. And this is actually the 1/1 result I mentioned in the previous slide. So we said that we are always using kind of linear combination of the control points. Once it's a linear one, but if you have higher order, let's say splines, then we need to use such blending functions. And the blending ones, as the name implies, we are not just purely having the average of these points. Instead, some point may have more importance, some other control points will have less importance. And that value, that importance actually will change according to your t value, the parameter value. So in our linear case, again, we can have a different representation, but the same line. And right now we are going to use basis functions. And this is the first basis function and the second basis function. So if you look at let me jump to the previous slide. Oops, yeah. Here you see actually the basis functions. This is the first basis function. This is equal to B0 of t, 1 minus t. Please keep this in mind. And the other basis function, which is B1 of t, is equal to simply t. And these are the basis functions. So by using them, you can obtain the final spline, final representation of the spline. Now let's have a look at this one. As you see, this is 1 minus t line, and this is just simple t line. And these are our two basis functions for the linear, piecewise linear case. But now we will make it complicated. We'll try to actually obtain some representations for the cubic splines. And for the first one, we will be focusing on the Hermite splines. And this is one of the fundamental type of splines in literature. It's very simple, not complicated. What are the constraints? The constraints are the endpoints, starting and ending points, P1 and P0 and P1. And then we have the tangents. As you see, this is the tangents, T0, tangent T1. And we may have, but if you just keep the start and end points, by simply modifying the tangents, we may have various cubic splines. They are all cubic, but obviously not the same. The tangents are affecting the profile of the splines. So what we do, I'm not going to discuss the details since in the last lecture we discussed the details. We are using the constraints to find the coefficients. Since it's a cubic spline, that's why we have A, B, C, and D, 4 coefficients. Now by using the constraints, we will find the representations of these coefficients in terms of constraints. For the t is equal to 0, we have x0 equal to d. And if we do the same, since this is a tangent equation, again, you can obtain c in terms of the derivative of the first endpoint, which is the starting point. So now d and c are represented in terms of constraints simply by x0 and x0 prime. And we can do the same for the endpoint by simply using 1 here. And we have a kind of an equation for the derivative equation. This is the result. And now by kind of solving these equations, we can clearly see that A is represented in such a form: 2 times the starting point minus 2 times the ending point plus the derivative of starting point plus the derivative of end point. And we have a similar one for B. For C and D, we have simpler expressions. But now we can have a kind of a matrix representation by using this relation. Since we have the control points as our start point, end point, starting tangent, and ending tangent. So by using them, if you have a kind of an matrix here, you can obtain the final spline. Any questions, guys, up to this point? Okay, that's it. Actually, that's the representation. We need to obviously multiply with, I forgot to write it in the previous slide, but since we have parameters, we need to multiply with this parameter, let's say vector here. And at the end, we will have the spline represented in such a form. And these are all basis functions. And you can obtain them by simply multiplying the first matrix and the second matrix. So that's the result. And if you look at the coefficients here, the rows are actually representing the coefficients and the columns are representing our basis functions. So for instance, I think this one should be B0, right? You can simply write 2 times t cubed minus 3t squared plus 0 times t plus 1 times t to the 0. That will be one of our basis functions. And you can have a look, you can easily write all the basis functions using the variables in the columns of this matrix. So these are the basis functions for the Hermite splines. We obtained them in the previous slide, as you remember. And now we will switch to Bezier curves. These are the things, the fundamentals of Hermite splines. By now we will make use of this information to obtain Bezier curves. In the Hermite ones, we are kind of actually mixing points with the vectors, which is quite weird. So right now what we are going to do, we'll just have points to represent Bezier curves. And we have some modifications here while switching from Hermite to Bezier splines. What we do, if you remember, we had tangents, and this tangent was in Hermite splines. It was represented as T1, but right now, in order to have kind of points here, 2 more control points, we need to have this T1 reversed. And now we will have such a segment between them to obtain the piecewise, let's say, representation of the control points. But obviously, since we are looking for an third order spline or a cubic spline, we need to do some computation. So that's it now. And as you see, we have different, let's say, variables. This is a starting point. And then we have Q1, Q2, Q3. Obviously, these are equal to each other. Q3 is equal to P1, but we need to have a representation for Q1 and Q2. And we will take this actually number as granted, and this is obtained for, let's say, constant velocity. In order to obtain constant velocity on this curve, we need to use such a number 3, and there are some derivations, but I don't want to spend time on it. So we can represent T0 as T3 times the difference between the end point of that and starting point of that line, Q0. And it's also the same for T1, as represented as 3 times. This time, since we have a minus sign here, so that will be Q3 minus Q2. So let's have a matrix representation of this conversion. So on the left-hand side, as you see, we have the control points of Hermite splines, right? And on the right-hand side, we have the variables of Bezier curve, and this is the relationship between these control points. So we can simply actually use the representation, matrix representation of Hermite curves, and then do some multiplication to obtain the representation of Bezier curves. So this is actually what I mentioned. So the coefficients can be represented by simply multiplying the previous matrix obtained. This was, this is equal to, if you remember, P0, P1, T0, and T1. So this is actually just simply a replacement. And now we will multiply these 2 matrices together to obtain new coefficients. And they are still our A, B, C, and these rows will give us A, B, C, and D. And now this is actually the Bezier matrix. These are obviously our parameters, and this is the Bezier matrix. And this part is called as Bezier matrix, and you can easily obtain the basis function for the Bezier splines. These are the basis functions. You can easily obtain them. As you see, the last one is not complicated, it's simply t cube. Or we sometimes call them as Bernstein polynomials. These basis functions are named as Bernstein polynomials, and they are represented with such a factorial form, binomial actually, and you can define any kind of basis function for any degree. Since this is just defined for third order, this matrix is giving you the basis functions for cubic splines, but by using the equation of Bernstein polynomials, you can obtain the Bezier curves for any degree, for any higher degrees. In questions, guys, up to this point, how we made the conversion between Hermite and Bezier splines?
Teacher, in the Bernstein polynomials formula, the first nk, is it a matrix or?
No, I will show it in a moment here. So it's just a combinatorics. So you can, this part is actually the first part you were asking. Okay, this is nk. If you see such a letter underneath each other in parentheses, then that means it's a combinatoric, and you can do it by using the factorials, n factorial divided by k factorial times n minus k factorial, and the rest is the same with the previous part. Okay, this is I'm sorry, this one is represented by using the combinatorics. So now you see we have the basis functions plotted here on the left hand side. These are the basis functions, 4 basis functions. Can you tell me which one is the fourth one? If you remember from the matrix, we had the last column as t. I'm sorry, this is not obviously t3. It should be t cube. And this one, the CN one, is the last, let's say, basis function. And by using these basis functions, you can represent the spline, the cubic spline in Bezier form. Now we will have a look at another way to obtain the Bezier segments. This time, we are going to actually draw it. We will not use any matrices, any calculation. We will simply draw it. So what we do, let's first focus on the linear spline segment, and then we will increase the order. Then we'll have a look at the quadratic and then do it for the cubic one. So what do we have for a linear segment? Obviously, we have just 2 control points, right? And this is the linear segment. And then if you want to determine any intermediate points, what do you do? We have a kind of an doing blending operation, and we may use such weights. These are alpha and beta. Since this is linear, if you are looking at this point, you can say that this part is equal to alpha, and this part will be equal to 1 minus alpha. Or we can say that this is also equal to beta. So by using them, we can blend the control points to obtain the intermediate points. So this is how we obtain the linear spline. Piecewise linear spline, a very simple representation. So any intermediate point is represented with the weights of these, let's say, alpha and beta. They are multiplied with the control points. A is the weight of starting point, and beta is the weight of the end point. By using it, you can determine any intermediate point. Now let's have a look at a quadratic case. This time, we will have 2 piecewise linear segments, which means that we will have 3 control points, right? 3 control points, and we want to obtain a quadratic curve by using these, let's say, control points. For instance, that might be the result. And again, we will follow the same approach, but this time we will be blending the results of linear segments. So how we are going to do, let's say we will have a point here by using the same alpha and beta. We will have another curve here, for instance, for same alpha and beta. Let's say alpha is kind of 0.25 and beta is 0.75. And it's also the same for the left-hand side. So that is the point we are looking for. And then what we do, we draw another line between these new points. And then in the last step, we are going to obtain the same point for same alpha and beta point values. And that will be here, since now this is the, again, 0.25. Alpha is again equal to 0.25. So that is now the new point should be on the quadratic curve. Okay. And if you do it for many times, you can obtain such points. And lastly, if you connect these points together, you will obtain the quadratic curve. And that will be quadratic Bezier segment. So here you see, for instance, this is, let me write how we obtain it. So I can say that this is P0, this is P1, and this is P2. So what we do, we obtain P10. It should be in between this point. This is P10. And then we need to obtain P11. It's between P1 and P2. Assume that is here. This is P11. And then by using this time, as you see, P10 and P11. So we are not using the initial control points. Instead, we make use of the intermediate control points, and this is P10 and P11. So we connect it, and we obtain such a point. Okay, and that is called as P20. And we can simply represent it. If you put all these equations into the final equation, you will see that it is a quadratic equation, and it's now represented by the control points P0, P1, and P2. Okay. Any questions, guys?
Teacher, are we always saying the coefficients are alpha and beta for every quadratic spline?
Yes, you can use different names, but you should have 2 variables at least.
2 variables for each spline.
For each linear case.
Okay.
But you see, in the quadratic case, actually, we have, you may represent this one as A, this one as B, and this one as C. So in the quadratic one, obviously, we need to have 3 variables, since this is kind of t squared, kind of t, and t0. Okay. You need to have 3 coefficients, but in this one we have there's a relationship between them, since we obtain them by using the linear segments. So that's why we have alpha and beta everywhere. But in general, you need to have 3 coefficients for quadratic curves and 4 coefficients for cubic splines. So depending on the order, you may need to increase the number of coefficients. Any other questions?
Yes, Hocam, I don't understand how P0 represents t squared and so on, and P1 represents t.
This is just a general representation, not related to what we have drawn here. this is just P of t is represented with such an equation in general. But it's not related to what we have done above. Just I want to show that the quadratic curves need to have 3 coefficients.
But I mean, in general, P0, P1, P2 are single numbers, or they're points, or they're variables, or
They are points. They are control points. As you see, they are in bold representation. They have x and y coordinates. Okay. These are the control points. P0, P1 is here, another control point, and P2 last control point. Okay. Any other guys questions? So here you see the representation in a better form, but the same issue, same thing. I can now say that this final quadratic curve is obtained by moving, actually, by doing this operation many times. For instance, assume that I have a kind of a point here. In that point, alpha might be equal to, let's say, 0.75 and beta is equal to 0.25. And I do the same for the piecewise case between P1 and P2, and then that will be in, I think, around here, right? This is another point. So what I do, I will simply connect this together. Oops, it's quite difficult to draw. Oops. But that should actually touch the curve somewhere there. Yes, that's it. And if you again find the, let's say, point on this curve which alpha is equal to 75, then that will be somewhere here. Okay. And if you do it for, let's say, n number of alpha values, then you will obtain such points. And finally, if you connect them, you will obtain your quadratic curve. And as you see, we haven't done any computation. We didn't do any matrix multiplications. By simply drawing them, we obtained the quadratic curve. And what do you think? Can we do it for cubic segments? So obviously the cubic segments are a blend of 2 quadratic segments. So once you, let me draw 4 control points. So in order to obtain this final cubic segment, what we are going to do, we need to obtain first quadratic segments and then join them together, join them in a different way, in a similar way to the quadratic case. So let's say, assume that we are working on this 2 linear case first, and let me use a different color. And if you do the operations in the previous slide, we'll obtain such a curve, okay? And then we can do it also for this one, this linear part and the last linear part. And I will obtain such a quadratic curve, okay? These are 2 quadratic curves. So if you somehow blend these quadratic curves together, then you can obtain the points for the cubic segment. So what we are going to do, for instance, again, we will be using a similar, let's say, approach. In the you will assume that alpha is, let's say again, 0.25, beta 0.75, and you do it for this linear part is here, it's here, and now we obtain such a curve, and I know that that's on the quadratic curve. And then I can do it for the other one, for this last linear part. That should be around here. And you need to do kind of a connection. So these two, ticker points are on the quadratic curves, okay? And then what do? You again join them and get a point here. Again, using the same values. And this point should be on the cubic segment. Okay. Since we are blending two quadratic segments. And if you do it for many times, then you will probably obtain such points and join them together to obtain the final cubic segment. Any questions, guys? Okay. Then obviously, as I've drawn, we have 4 control points. We are interpolating on each quadratic part, again, using alpha and beta, and we are blending the results, again, with the same weights.